Okay, so more about line integrals. The definition of this, certainly whenever you do computations with numbers that, or rather functions that you cannot integrate, there are always a possibility. Then you go back to the definition, which is the Riemann sum, and so every Riemann sum serves by design as an approximation. And if you're doing any kind of computations in practical circumstances, that is the way to go. In the meantime, if we do anything with that requires theoretical development and infinite accuracy, then that's where we are. And as you can see, it's kind of uncomplicated. The confusing part often is, in fact, the notation on the left, because there are several similar definitions that line integrals that have to be unwrapped into what you've got on the right. So we already had one. We had this is line integral of a vector field. Then there was a line integral of a scalar function for the mass, remember, and there was even the integration of a parametric curve. So all three are different, and all three have different notations. So I'll get to that today. So just to compare them, because there is number 4 as well. In the meantime, the only one at this time meaning behind it is the work. And but mathematically, this is what it is: a pretty much composition of two functions, vector field and parametric curve, which produces nothing but composition produces what is it? Vector valued. It's still a parametric curve, and but that extra term over here takes into account the derivative, or how fast you're moving through that curve. However, the result is independent of our parameterization. Okay, the only thing matters is the direction, one or the other. That's the whole thing is right here. Okay, so just for a little practice, we had examples. One example: constant vector field as well as constant, or rather straight line for the parametric curve. Then you end up integrating a constant, which naturally produces a constant number as the answer. So the answer is always a number. Now this whole example, the last one, was intended to see what we can do when we approximate a situation that either, well, as you can see, the vector field has sort of discretized or sampled for us in all the nodes of our grid. There's a vector, and now we have a path through it. And then in order to, since there is no formula, there is no, then the integration will be not happening. So we have to pretty much go back to the Riemann sum, or in this particular case, you don't even have to go to the Riemann sum. I guess that I misspoke there, because if you go back to the original definition, the original formula that we're dealing with, these are in the box, the total work is not a Riemann sum until we tweak it a little bit in order to end up with a Riemann sum and a Riemann integral. That's what happened in the next line, and that's how we got the definition. But if you're doing computations, then this, what's in the box, multiplying the displacement times the dot product with the force, that gives you the answer. So that's what I would suggest, rather than trying to go back, rather than you using or trying to discretize this integral that we have in the definition. This one, instead, we'll just go straight all the way back to the definition and just do summation. The only thing that's missing is we have to sample our function as our curve as well. Okay, so which means that we have to pick a few points on the curve. Ideally, they would have to. Actually, we do not have any. But ideally, if the curve was passing through the nodes, then we would have a match up with the with the vector field, but we don't. So we have to make decisions, and so probably one per square about that. So I would have. So I'm trying to sample my curve, and then I'm taking. I'm moving through my curve, and then I'm picking points, the nearest point on the grid. So this is one, this is the other, and this is the next one, and this one, and maybe this one, and that one. Okay, so in that order. So these are the sample points for my curve, and they will give me the displacements as well as the samples for the curve and for the vector field. So to make that point clear, I wish I could. Yeah. So if I can copy it. Okay. So I'll try to erase things that we don't care about anymore. So everything but the sample points will have to go. Okay. So sample points and the vector field vectors of the vector field at those points. So these are still necessary. This is not, and this is no interest to us either. Okay. So no, that's not interesting either. This is interesting. No, not much. Like this. Okay, so as you can see, these are the only participants in our are going to be the only participants in our computation. These so we have 1, 2, 3, 4, 5, 6, 7 points, 7 vectors. 1, 2, 3, 4, 5, 6, 7 vectors. Okay, so yeah, so there is a bit of a mismatch here. We actually need only. No, we're going to be computing displacement. So, but we're going to need then only 6 vectors. So the first vectors will have to be ignored. So in fact, another thing that we're erasing is the curve itself. It is not. It's not doing us anything as long as we know the order of our motion through these vectors, through this square. Okay. So let's see. So once again, let me just draw the lines like this. So these are this is our motion. I hope the vectors are clear. These are the only vectors. So there will be one vector. So that one is actually of no interest to us because we need only 6. Okay, so let me go on from these. Okay, so let me just plot displacements and plot. Well, actually, I think it's better to match the order of operations. We put the force first and then the displacement. Okay, so I put the force here and the displacement there. Okay, 6 of them. So the force is, so once again, this is the starting point. Starting point for the vectors, but not for displacement. Displacement is, so the force is 1, 1, okay? And the displacement is also, coincidentally, is 1, 1. Okay, so once again, from this point, I move diagonally, and I'm recording the displacement as 1, 1, and I'm recording the vector, which is the next one. This is the vector, also 1, 1. Okay, and then, okay, and I just keep moving. What's next is the net displacement is 1, 0, 1, 0, and let me just record them. So I'm looking at green ones. Let me just look at the green ones. 1, 1, 1, 1, 0, 0, 1, 0, negative 1. No, wait a minute. That's not right. This is 0, 1. Okay, so that vertical part is 0, 1, then it becomes 1, 0, then it is 0, negative 1, down, and then diagonal it will be 1, negative 1. Okay, so these are the display. Okay, so I meant displacement first. Sorry about that. So let me start over. So these are the displacements over here, and over here I will be putting my forces, the red one. Okay, so as I said, 1, 1 is the first one. The second one is 1, 0, 0, 1 again. So we follow the same direction, but the next one is 1, 1, and then 1, 1 again, and finally 1, 0. Okay, so dot product here. So it's 2, 1, 1, negative 1, and 1. Does it look okay to you?
Are we missing a displacement after the one?
I did miss. I need 6. I missed. Which one did I miss?
I think it's the one. So we've got 1, 1, 0, 1. I think we need.
Let's start with the displacements. 1, 1, 1, 0. I'm sorry. 1, 1. I missed the first one. 1, 0. Yeah, so I missed it. No, the first displacement is 1, 1. Okay, the next one also 1, 1, right? 1, 1, 1, 1. Okay, 1, 1 over here, 1, 1. Okay, now the, let me erase this just in case. And then we have also 6 forces. 1, 2, 3, 4, 5, 6. Which one it is? So 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 3 1 1s. Okay, so now we have to align them appropriately. So this is aligned like this, like that. Okay. So 6 edges, 6 forces, 6 displacements. Okay, so this is 2. 1, 1, and 1. Here it is 1, and here it is also 1. Right? This is negative 1. 1, 1, negative 1, 1, 1, and 2. Okay, so all right, so we're not doing anything with these. We just add those, the dot products, and so together it gives me 5. Okay, so as you can see, the force or the work as it estimated on each of these edges could be positive, could be negative, could be 0, and we have a lot of ones and a lot of zeros. Sometimes when you look carefully at your vector field, you might actually determine not the answer, but at least say whether it's positive or negative. So that kind of skill is useful. So for example, if you have you are moving straight along a straight line, and my vector fields might be very random. Like this. Okay, so once again, this is my force field, and this is my displacement, or that's my parametric curve, or rather, P of T. Okay, so work. What can you say about the work?
It looks like it's positive.
It looks like a positive because why? Because our displacements are, so how should I put it? The angle between each d, the displacement, and the corresponding, or each f is between negative pi over 2 and pi over 2. Okay, so it is not, so at no point the force pointing in the direction opposite of our displacement. When it is a straight line, it is very transparent, but you can certainly, so the answer is indeed positive. And there is one of them possibly even 90 degrees, but we know that's not, it does not contribute to anything negative. But you can certainly imagine that even if you have a curvy path, then you can still imagine that looking at it one point at a time, zooming in, and you can observe a similar situation if you're careful. And so once again, you might be able to discover such a behavior. Okay, one example. So that's another example of the same pattern of behavior. An extreme case of this is what if my vector field is tangential to my curve, like this. So once again, the work will be, in either case, will be positive. So once again, so F is collinear. So not only it is parallel, but it is to P prime, collinear with the direction of the curve, which is its tangent vector. Okay. So incidentally, in the last case, if I look at my formula, then that what I end up with. The formula of the definition of our integral right there, it is a dot product of P prime and F. And then what is going to happen? Well, hypothetically, what if? So what if F is equal to P prime at each location? And then what does the dot product look like then? F dot P prime.
Which is the magnitude of P prime?
It is the magnitude of P prime squared. So that way we are halfway, almost all the way to the case of computing the arc length. I mean, it's what is this like? It's like, well, imagine you are walking through like a pipe, and there is maybe water, and water resistance is the force that you're dealing with. Okay, then if you know how much work you have expended, then you will know the length of the curve roughly. So it's pretty much almost the same thing in that sense. So on the other hand, we could see the opposite, and that is what if F is the gradient of some vector field, some function of several variables. So remember, the gradient is a vector field. So suppose that the vector field we have been talking about is gradient of some function, the gradient of some function. Then suppose, so that's question 1. And what if the second condition, P is a level curve? Then what? What's the relation between the gradient and the level curve?
The work is going to be 0 because they're
Because they're, yeah. So these two will be perpendicular. Not these two, but the tangent to our curve and the gradient will be perpendicular. So we conclude then at every location the dot product will be 0. So the work is also 0. Okay. So these are kind of clues you pick up to be able to answer some of the questions about the work and on the line integrals. Here's another example of more specific. And suppose we have our level curve, just a curve that we pick, a closed curve. Okay, closed curve meaning that beginning is the same as the end. closed curve. Beginning equal to the end. Okay, so you still have to indicate that point, that which is simultaneously beginning and the end, and also in this context we'll also need orientability. That's why, oh no, the orientability, but the orientation, and the orientation has to be indicated simply by an arrow. So that would be an example. I'm picking the single unit circle curve, so that's my C. Okay, and then, so once again, no parameterization to worry about. And then say my force maybe, my force field looks like a constant one like this. So as you can see, unlike these examples that we saw, it varies all the time. The force, the direction of the curve and the direction of the vector field vary relative to each other all the time as you move through the curves. Unlike those examples, or tangent or perpendicular one, so that's neither one. So any thoughts about what W could be?
Would it have to be 0 because the positive and the negative bits would
yeah, so that's right. So the work will be 0, and indeed it is because of the cancellation. So it's not because the work is 0 at every point, as one of the examples we just saw. So it is just a work 0, work 0, work 0. So the whole thing is 0. This one, if you take any smaller piece of the circle, smaller than the circle, the whole circle, the work will not be 0. But you can match up points, the diametrically opposite points on the graph of on the circle, which will produce different opposite contributions to our work, such as say this one and that one. Okay, so as you can see, let me plot the tangent for you. So this is the tangent, for example, and that is the tangent. Look at it. So they're opposite, and then they become collinear. Okay, so then they will naturally. So it's the same thing, the same two identical vectors. Well, it depends on our parameterization, but suppose just to make that case, and we know the theory that it is the outcome should be independent of our parameterization. So it is up to us to choose the simplest parameterization we like. So just as well, we can take our parameterization to be sine cosine or cosine sine. So that could be our P of t. Okay, so then the opposite, the diametrically opposite points will have the opposite tangents, but identical vector field because it is constant. Okay, so and that way you can match up all a number of these points. As long as they're diametrically opposite, the relation between them will be opposite. Another way, you can just cut it in half and estimate the and just let's just leave it as is, so that once again you count cancellation point by point, which is not exactly what happens when you do integration. But if you do your Riemann sum appropriately, you can actually cancel it one by one, and then the limit will be once again 0. So all Riemann sums are zeros. If you choose them appropriately, then the limit should be 0 as well. Okay, so that is sort of an estimate or what is it, a guesstimate. So we guess, and we can provide a good argument why it is 0. But really we can carry out the computation. It is simple enough for us to carry out the computation all the way through to confirm that the work is 0. So the parameterization is here. P prime is, well, certainly should start with specific values for t. Otherwise, you don't know what to integrate or whatever your integral duration is. Then you need your derivative, which is, as we know, negative sine t cosine t. Okay, so that will be part of our integral. And then, according to what I chose here, my force field is simply 1, 1. And you can probably guess that it doesn't matter what that vector is. I could pick any vector, and they should produce 0 as well. So anyway, the work is the integral. Let me use the notation carefully. Dot dp. Once again, capitals indicate vectors. Yes. Over c, the unit circle. By definition, it is written as integral after the parameterization is chosen. I will have f of p of t dot product p prime of t dt. Okay, substituting, it doesn't matter, the first term, it doesn't matter, it will be 1, 1 no matter what. So integral from negative pi to, from 0 to 2 pi, 1, 1 dot, p prime is negative sine t, cosine t, dt. So once we dot product is done, this is calc 1 integral. So it will be negative sine t plus cosine t. Okay. Integrate. Okay. Integral of sine. What's the integral of sine?
Negative cosine.
Negative cosine, so I have cosine t here, I have negative sine there. The limits are 0 and 2 pi, and well, it will be 0. Just subtract 0 minus 0. Okay, so that's a typical example. Once again, if you think about it, in fact, let me write it this way: 0 minus 0 is equal to 0, to indicate that both of these terms actually produce 0. It's not they cancel each other, cosine and sine, but rather cosine produces 0 and sine produces 0. Why? Because both of them are 2 pi periodic. Okay, so which means that if I want to, I could put here, say, I don't know, p and q, any vector with any 2 coordinates, and everything will work out in the exact same manner. So it will be simply p and q over here, and once again, they will just serve as extra coefficients of cosine and sine, and once again, a periodicity of all these 2 functions over integral 0 to pi will give us 0. So it doesn't matter which way that vector field points. It will give you 0. And then certainly an interesting question is, what if you wiggle that vector field a little bit, and what if it's not exactly a constant vector field? So maybe they kind of goes sideways. And the question is it still going to be a 0? Okay, so the answer will be answered shortly, and you might remember what the answer is. And the answer is has something to do with the vector field being irrotational. And to make that case, let's change the vector field to a rotational vector field, and then we'll realize that, well, even though we make a round trip, the work will not be equal to 0. So that does not have to be necessarily the case for round trips. So round trips is a very convenient tool, as we already are starting to see, for studying what? For studying vector fields. So, and it will be a way to distinguish those vector fields, classify those vector fields. So what I was going to do is to replace this vector field, which is constant, doesn't matter what it is, and then replace it with a rotational vector field, and you already, well, let me start over here. So the next example, so F is rotational. So what is the, so you remember the rotational vector field? What does it look like? So they follow the, they seem to be as kind of, if you make the vectors small, they will follow the, seemingly at least, follow a circle.
Is it negative yx?
negative y, and x, yes. So that would be, these is choice, these is vector field that is rotation. Remember that the property of this vector field that we have found is that, what is that we found about? It's that it fails the, what test does it fail?
Gradient test.
The gradient test. So it could be, it might be gradient, but it turns out, which is what we're gonna demonstrate eventually, that it's not a gradient vector field, which we kind of guessed with the idea that you cannot walk up a surface and then end up on the same height or altitude on that surface. And then what we do is it's actually becomes quite simple, and they already has been discussed just recently. I choose C is still C. I'm studying this vector field, which is, by the way, is longer as we move away from the zero, and it is smaller and smaller vectors, so smaller and smaller as you move, as you stay close, and it is 0 at 0. Okay, so it doesn't matter because we only care about one single. If we're studying one parameter curve at a time, and so one of the parameter curves that we pick is the, once again, that unit circle, and we carry out the exact same operation. And what's especially good about it is that there's a match of what we just talked about in the a minute ago, and that is the tangents match in direction match the vector field. So which one is it? This one. On one hand, it is tangent, right, over to our circle at this point. On the other hand, it is also our vector field, right? So the direction will be always the same, but let's make it specific. I have my p prime. This is c. Once again, it is p is equal to cosine t sine t. So that is my c. P prime is equal to negative sine t cosine t. Okay, and then once again we look at the work integral over c f dp, and then let's carry out. This one is there's some computation involved, but I'm writing the integral from 0 to 2. Well, let me write it out, the definition. So it will be f of p of t dot p prime of t dt. Okay, substituting things. So the first term inside will be a now variable. Okay, so integral from 0 to pi, and so let's just doing plain substitution. So they we have to match. So see, I'm substituting p. Well, I'm substituting p, which is this one. This p is substituted into f. Okay, how? Not replacing things, but rather identifying things appropriately. This is x, and this is y. So we have a formula for x, and we have a formula for y, and that is what x and y are being replaced with in the formula for the vector field. Okay, so what do I write here?
Negative sign.
Negative sign. Negative sign. Y is sine, so negative y becomes negative sine t. Okay, and the second term of x, I'm looking at f. Well, I'm looking at f because that's where I substitute p. So the second term is x. The second component of the vector field is x, and x is cosine t. Okay, and multiply by p prime, negative sine t cosine t dt. You can see how things match up. So it will be sine squared t plus cosine squared t dt. What's the answer?
2 pi.
2 pi. So this is 1, the sum of the squares, and the answer is 2 pi. So what happens if we pick, now that seems, if we really want to study the vector field in the same manner as we have studied functions or several variables by means of parametric curves. So one way we studied parametric curves was the directional derivatives, and it worked out pretty well. However, we picked a very narrow class of functions, so straight lines through one point, and that tells us something about that's happening around that point on the graph of our function, say 2 variables. Now, that doesn't work out anymore because, as you can see, we're gonna be looking at once again to study vector fields by means of parametric curves. What parametric curves do we pick? And we pick closed ones. Okay, so closed ones to begin with, but then there are really so many of them, and the question becomes how do you check them all simultaneously? That worked out nicely with the straight lines because they are very easy to put in give them one description. But you just look at all the circles; they can be located elsewhere. They can have different radii, and then there they have what about weird shaped curves. So it's not that simple. But you can certainly see what happens if I change the radius of the circle. There is nothing special about the radius of the circle that produces 2 pi, and you can see that what would happen. Not really much. Not much would happen. It is p prime would change, and it will be simply a multiple, right? So if radius is 2, then I'll have an extra coefficient 2 here. That's all. So p will be larger, and over here too. Yeah. So it actually quadruples. So if you increase the radius by 2, the work quadruples. It's only the reason for that is not really because not only the shape changes, but also our vector field. Remember, its vectors grow away from the origin. So if we had normalized our vector field, then the growth will be the work will simply double. Okay, so that's what can happen, and we can carry out those computations, but really not to the degree that would in some way be conclusive. So we'll get back to that, but it is an indication. If we just review this result and see what it tells us, it really brings home that idea of rotational, irrotational vector fields. Taking those trips up, back and forth, round trip uphill. Okay, round trip uphill. What are we talking about? We're talking about work. So if you go to school uphill and then go home uphill, then you work both ways, or the gravitational force works both ways. So, and it seems impossible, but that's because the gravitational force cannot have that because it's different. It is a gradient force and gradient vector field. But this is an example of a round trip that requires positive work to complete. Okay, so once again, so if it is about gravity, that's not the case. Up and down, positive, negative, it cancels out. This is not. So once again, it's easiest way to think about is there is a whirl of wind or some kind of accelerator or whatever, and you're going against that pressure, and to complete the circle, you have to have expanded a positive amount of work. Okay, so that is to be investigated further. But at this time, let's just look at a slightly broader view of line integrals. So line integrals versus the algebra of vector fields, because remember, vector fields are subject to the algebra of vectors, and now we can easily answer the question: what happens to the work if you do algebra with vector fields? So what I mean is, you can d plus w. Okay, so you can have two vector fields, and it produces, if you add them together, it's simply like adding force. Remember the metaphor in this setting for vector fields is force fields, and so you certainly can have two forces of different nature acting on the same object, gravity plus electromagnetic plus spring or anything, or friction as well. Well, friction unfortunately depends on your speed usually, so that we don't bring it into this, so because these are entirely location dependent vector fields. So location dependent vector fields, you add them together, two forces, and you need a new, and you create a new vector field. So what happens to the work if you add vector fields? So in other words, okay, so I'm afraid I'll have to erase this because I don't want to mix up letters. So one force field is F, the other one is G. So, and I'm talking about F plus G dot dP over C. So once again, we are moving along a curve through a vector field, but this time the vector field is actually broken into two, and then maybe one like this, and the other one is might be different. Okay, so well, you certainly can guess what happens. It splits into two, and the algebraically it is very predictable, and the result follows from. You can either see it from properties of integrals as it is defined, or through the Riemann sums. So it's this sum rule, and the second one is, as you know, constant multiple rule. So a vector field can be, say, doubled or tripled, and nothing in that respect changes the setting, but the work does increase or decrease proportionally, changes proportionally. So all of these properties that are familiar from calculus 1 and before, or calculus 1 and calculus 2, they still hold. Should be surprising because once again they are just calculus 1 integral. Integrals no more, no less. So the substitution we're not going to talk about, but the substitution integration also possible, and so certainly also worthwhile. Another one, well, what other properties of integrals do you remember? I got asked this question before. So these two, substitution, what else?
What about the additivity over like an interval?
Yeah, I was driving at exactly additivity, which is when you do not add functions, or in this case vector fields, you add their domains. Okay, so what I'm talking about is then what if you have two curves? Okay, whether they are, and they suppose they form a new curve like in a consecutive manner. So this is C and this is K. Okay, so you're moving consecutively and they have only one point in common. Then what happens to the work? And once again, it is very predictable. It will break into two once again. Okay, so it's exactly the same as the additivity property from calculus 1 when the domain is splits into two, and that's what creates. That's what additivity is called, as opposed to sum rule. So sum about summation of functions, the integrands, and here we're talking about the splitting of the domain of integration. So that brings me to something, to this little classification, or at least some kind of taxonomy of integrals with parameter curves that we have had, and they have a different nature. So we had three. So let me write them up, and there will be, there are 3 already, and there will be number 4. So I just wanted to see that the similarity as well as differences between them. Number 1, actually, if we go all the way back to September, how did we integrate parameter curve? Do you remember?
Oh, just component by component, right?
What?
A component by component?
Yeah, it is component by component, and say P dt. The meaning behind it, or metaphor behind it, is the same. Could be, say, you have your velocity and you're looking for position. Okay, you integrate your velocity, you get position. Okay, so if P here is velocity, then its integral will give you or displacement rather. So see, what's behind it is displacement. Okay, so how different this is from what we have been doing is next is the next one is arc length, and the notation is over curve. What is it? F ds. Okay. Let me write it out. Suppose we have parameterized C, then we have integral from A to B, f of P of t, P prime of t, dt. Okay, so the crucial difference here is where the place of the parameter curve. The place of the parameter curve is what just came up a minute ago, is either integrand, or over here it is in fact, if we ignore what's on the right, where the parameter curve ends up is the domain. So either we integrate the parameter curve in case 1, or we integrate along the parameter curve something else. So we're integrating a function along that parameter curve, and that's case 2. It's a very different line integral. And the third one is the most recent, is in fact what sort of totally fits into the pattern with number 2. It is f dot dp. Okay, so integral from A to B, f p of t dot p prime of t dt. Same thing. Once again, the C, the parameter curve. Where is parameter curve? It's in the domain, not in the function. It's only when you get to substitute things, then you end up with the parameter curve becomes visible, but otherwise it's hidden inside of an actual curve. So, okay, we'll talk a bit more about that.